I'm Al Globus, and I did some of this work with some collaborators in Romania who were involved in the Space Colony contest. And I'm going to give a talk which is the exact opposite of the one you just heard, which I thought was great, by the way. He was talking about this enormous project that looks really cool. What I'm interested in is what is the smallest possible project, space solar power project, that could possibly turn a profit, and how much R&D do we need to get there? And the reason I'm interested is that the folks that criticize space power, at least some of them say, you shouldn't even put in R&D because it's so hard and we need so much R&D that it can't possibly pay off, even though there's a huge payoff. And what I'm trying to do is show that they're wrong, even if not all my numbers are correct. And I'll tell you right now, they're optimistic. So there's three technologies it takes advantage of. A solar sail, developed by Japan, in orbit, on its way to Venus today. We know it works. Infrared power beaming, which has been demonstrated at small scale by this vehicle here, and fiber lasers. So, next slide, please. So here's how I see the SSP problem. It is a high-risk, huge payoff energy investment. It's high risk because it's difficult, it may fail, could cost a lot of money, but if it works, we get all the power we could possibly want for billions of years. Okay? There are two classes of energy research in this area. There's fusion, it's also very high risk, high payoff, and SSP. Fusion has been going on for decades. They've spent tens of billions of dollars. They spend about $100 billion of federal government money a year. They have never produced a single watt of power above what has come in. And if things go really well, bit has been demonstrated at many frequencies and over different distances, yet for some reason, that's what we spend on the research in the federal government. It's more in Japan. So what I'm going to try to do here is show you that if you look at a simple single launch system, that there's a fairly minimal R&D program to get you ready to start building it. And the target that I'm aiming for is 100 grams per meter squared of collecting area, 10% end-to-end efficiency, one Falcon 9 launch, modified for the heavy, because I found out fairly recently. If you work through the numbers, and if I haven't made any terrible mistakes, which is there's no guarantee is the case, you get 120 meter radius sail with thin films using fiber lasers for IR beaming. You get a figure of merit is mass per unit of power to the grid, because that launch cost is a big piece. So we come up with 720 grams per kilowatt, get about 6 megawatts to the grid, and the idea is if you can sell that to certain high-priced niche markets, that you can pay for the launch, because I know how much the launch costs. I don't know anything else. You can pay for the launch in a year, give or take, and you don't want to start until R&D on the ground has got you about a factor of 5 better and the efficiency that we think we can get out of the components. Next slide, please. So here's the problem as I see it. Space solar power for 30 years has been chasing something like this. Something very, very big. And because it's big, it's hard to do. Okay? And the reason it's big is because these microwave antennas need to be 1 kilometer or so across. Now you can fiddle those numbers, but they all come out to be very big. If you take advantage of some of the windows in higher frequency, you can radically reduce that size. It's been demonstrated that you can actually deliver that power over at least some distance. And if you take advantage of thin film solar cells, which actually are on this vehicle, this is the vehicle you come up with. Something small, single launch, hopefully, and not too expensive. Next slide, please. So, here's that same argument. The reason that the satellites, the antennas are big, and I'll repeat this for some of the people here that haven't been here for the last 2 days of sessions, is that the product of the antenna sizes is a linear function of the wavelength. And if you use microwave, say 12 centimeters, you can also get down to 3 or 4 centimeters, you end up with antennas this big, but you end up with some pretty good efficiencies. These are numbers from the stuff in the 70s, and John may tell you some better stuff in a little bit. If you have a kilometer scale antenna, it makes no sense to have a small array. You have to have a kilometer sized array. And you're making some reasonable assumptions, you get enormous amounts of stuff you have to send up into space. And what the critics will tell you is that there are multiple dimensions on which we need multiple orders of magnitude improvement before we can do this. Next slide, please. You need in-space construction. Slide courtesy of Boeing. This may be easier than I thought. I just heard a discussion. But you need frequency allocation. And that might actually turn out to be much of a problem. You need great big chunks of land, because even though you've got a kilometer antenna on orbit at GEO, you need 10 kilometers on the ground or something like it. And because this thing is an enormous system, you need some sort of advanced launch. This is a laser launch. Next slide, please. So the trick to it is you've got to get the size of the antenna down. And we're going to have to pay a price for that. And here's the thing. So this chart is wavelength by atmospheric absorption. And you see why people like microwaves, because you can get, there's very little absorption, and you can get a lot of power to the ground. The problem is you're in the centimeter range. There are some narrow windows in the infrared near the optics, near the optical, where there are windows in the atmosphere. And this chart, this is the opposite chart. So this is wavelength, but it's only for a small band, and this is transmissivity. So you like big peaks. So if you look at some of these peaks over here, they're not that far from 100%. You're going to pay a price, but because a micron is 30,000 or so factor smaller than centimeters, you get a huge reduction in the size of the on-orbit beam hardware. In specific, roughly, if you go with a 5-meter beam, you end up with a minimum ground receiver of maybe 32 meters or so. And for the 6 megawatts to the grid system, it turns out you don't even want to do that because you have too much intensity. Now there's those who say this 10 sunlight intensity that I'm working with is too much, and they may be correct. But even if you can't afford 10x sunlight, which will give you a 50-meter receiver, if you can go to 1x, it only increases the diameter by a factor of 3, because remember it's square root. So you're still something the size of a football field, give or take. Next slide, please. Okay. So IR has been demonstrated in at least one context. This is a vehicle which is climbing a tether, which you might just be able to barely see. The setup is that there's a helicopter holding up a tether. The climber is going up the tether, and there's an infrared beam coming to give it the power. Laser motive, there's a number of companies that did this. This capability has been demonstrated by more than one people. Laser motive happened to win. They use this specs. This is why I use 10x. It's just because they used it. It's nothing magic about it. But here's the thing. They were able to deliver 500 watts over a kilometer, not bad, at over 10% overall efficiency. High efficiency was not important to this task. It was useful, but it wasn't critical. So they didn't drive the technology as good as they could. If you talk to Jordan Kerr, or at least if you talked to him a year or so ago, and asked him, he's the chief engineer, the chief scientist of this organization, he told me that he believed that today, using today's technology, you get about 25%, and with reasonable near-term improvements, you get 40%, which is not as good as 63%, but it is probably worth a factor of 30,000 reduction in size. Next slide, please. So, the next step I want to talk to you is, how do you, if I'm only going to have 100 grams per meter of collection area, I need very lightweight collection area. This is the Icaros satellite on its way to Venus today. We know it works. If you look at this very faint yellow, those are thin film solar cells. They're up in space and they are working today. They cover a very small part of the surface. They are extremely thin. They're producing about 500 watts, which if you work out the numbers, maybe 4% efficiency. It's costing you about 45 grams per meter squared. Remember that 100 grams per meter squared? So we're into that. And it's generating about about a kilowatt for every 800 grams. So it's in the ballpark of what we want, but it's very low efficiency. And it's beautiful because we know it works in space, for sure. Next slide, please. So here's ground thin film. As you can see, you can handle them, you can move them around. These are much heavier than what we want because they have to survive wind and hail and rain and stuff like that. In the lab, people have achieved up to 20% efficiency. In the wild, meaning commercially, you can buy this stuff at 10 or 11% efficiency. They're fairly thick, they have a lot of mass, but remember they're packaged for Earth, and you can roll them up. Because this whole system's going to have to be rolled out, stuck in a launch vehicle, and sent up into space. So you have to be able to make it small. If you make assumptions about taking this technology and putting it in an environment where there's no wind, then you come up with 20% efficiency, 160 grams per kilowatt. just for the power collection. Okay, next slide, please. So here is the target system that I'm aiming for. Now this is a square last talk, and it'll probably change shape next talk, but this is a circle right now. So the other side has got the solar cells on it, which we just discussed. On this side, here's the problem. If you take the energy from the solar cells and you bring it all to the center, and you put it into an IR laser, lasers are not very efficient. So they will generate a lot of heat. And in order to get rid of that heat, there's nowhere near enough area. So you're going to have some sort of thermal radiator coming out this way, and you're going to have pumps to get the stuff. It's going to cost you a lot of mass, it's going to cost you a lot of complexity, and I don't have enough expertise to figure out how to do it, so I had to find another way. There is a class of lasers called fiber lasers. They are optical cable doped with rare earth in order to laze. They have the lovely property that you can buy them commercially at 100-meter lengths. So you can have your fiber lasers start at the outside and come to, emit down here, and they're going to emit all that heat over this entire region. And particularly if you put some conducting materials behind there, you can end up using the entire back of the sail to get rid of the heat. Next slide, please. So here's the thing about fiber lasers. They will laze at right around 1 to 2 microns, depending on what you put in, which is exactly what we want. Commercially today, you can get 50 kilowatts out of a fiber. You don't have to, no R&D, that's just done. 30% efficient, which is not too bad for a laser. We're going to have to get that up. You'll see that later. But the real killer is these great thermal properties. They're long, so you can get rid of heat over a lot of area, and they operate at high temperatures. And remember, when you're rejecting heat in space, it's a function of T to the 4th. So a little bit of higher temperature gets you a lot of heat reduction. They provide their own waveguides. At one point in this design, I had thousands of little lasers all over the place trying to beam to the center, and it was pretty obvious it was never going to work. These provide their own waveguides, take it to right to the center, no problem. And as an added extra bonus, I go into this more than I will here in the paper, if you make them a little thicker than you really need to, and you work out the numbers very conservatively, you can probably get rid of the rotation, which I forgot to tell you about. Icarus is a helium-got gyro. It has no structure to keep it flat. It rotates. Okay? The rotation doesn't hurt you for a solar sail because it's just bouncing photons up it. But if you're trying to beam power to the Earth, that means you have to counter-rotate the beaming hardware. And it turns out that the fiber lasers are stiff enough that you probably don't have to rotate. The fiber lasers that are not very stiff, but sunlight isn't very strong. That needs a little more work, and there may be better ways to do it because you have to make the fiber lasers thicker than you really want them to be. Next. So here's one laser. This is not even close to scale. So there's 120 meters. The fiber laser itself comes in 100 meters, which is commercially available, couples to an optical cable which loses very little heat because we need a swath about 1/3 of a meter wide in order to get rid of the heat at 340 K. And so that's what this swath right here is. Next slide, please. So here's the target system for the IR. Remember, it's a target system. There's probably some better way to do it. But this looks like it worked. Almost 400 lasers spread out 2 meters apart all around the outside. We already discussed this. Each one 35 kilowatts apiece, which is below what you can buy from commercially today. If you make them stiff enough so you don't have to rotate the sail, it'll cost you about 25 grams per meter squared. Give or take a little bit. For the heat rejection, you need to get rid of 230 watts for every meter. If you assume 60% efficiency, which is about double what you can really do commercially today, if you run it at 340 K, then it fits. It works. Okay? And this will cost you, if you use something that weighs about the same amount as very thin tinfoil, I'm not suggesting tinfoil is the right material, I'm just hoping that it's about the right mass, it'll cost you another 7 grams per square meter of sail, total of 32 grams per square meter. If you add that to the 45 grams per square meter for the thin film, we're at 77 grams per square meter, which is under our 100 grams per meter target. Next slide, please. So, here's the R&D efficiency, with the R&D challenge. Without doing this, you'll see a little bit, it doesn't actually make sense to start building. We need this first. If you take all the different things you have to do to get power to the ground, and you look at their efficiency, either in the lab or commercially, as is available, you get, if the numbers are correct, about, this is assuming the 42 here, about 2% efficiency. So 2% of the energy that comes into the sail shows up in the grid. which is okay, but it's probably not good enough for the markets that I'm hoping for. If we can achieve these targets, and the important thing is these two have valuable ground applications, so you don't necessarily have to charge these two to the project, then you can achieve about 10%. Now these targets are somewhat arbitrary, you can move them around, you can substitute them, right? But at the end of the day you want something in the neighborhood of 10 down here. Next slide please. So if you can do that, which is definitely optimistic, but it is not multiple orders of magnitude. And that's what the critics say. You can't do this because there's multiple orders of magnitude improvement in many dimensions. This is hard. This is not easy. And we might not be able to do it, but it is not multiple orders of magnitude off. So in any case, if you can do it, and you go with one Falcon 9 launch, which will get you about this much to geosynchronous transfer orbit, we assume you fly the rest of the way, for $56 million, costing you about $9 per watt for launch if you can pull this home. If you, this gives you one set of numbers, but I'm actually going to go with this seed. If you use a Falcon Heavy, you can put 5 of these in there. The reason you don't want to put one big one is because the fiber lasers aren't thick enough to keep the sail from folding out when you make it bigger. So for the purpose of this analysis, we put 5 of these guys in a Falcon Heavy. If we assume the highest price on the website, we're down at $4 a watt for just the launch. Now nuclear fission plants will run you about $10 a watt, depending on who you believe. But if you look at the price of the plants that are completed, the price is always much higher than the price of the next plant that they're pretending they're going to build really cheaply. So if you only consider launch, it's definitely competitive. This does not consider operations, building the sail, and so forth. This does not consider fuel, insurance, waste disposal, blah, 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 and so forth and so on. So if you go with the target system, remember 10% of the sunlight power to the grid, we need that R&D to get there. 100 grams per meter squared. We're paying 77 of that for what we already know. We have 1 ton left for everything else. Because we got to combine the beams, aim them at Earth, have the electronics, the fail-safe systems, the deployment mechanisms, the structure for the state. There's a lot of other things that need to go into this 1 ton. I haven't done the analysis, I don't know if we can do it. But as long as you don't miss it by too much, we'll still be okay. You get this figure of merit. Now here's what I love about this figure of merit, 720 grams per kilowatt. Steve Fetter, who's written one of the critiques, actually the critique of space solar power used by Pete Worden to demolish a friend of mine in a debate. What Steve Fetter said is this figure, what you can't do is 5,000 grams per kilowatt. That was his target. He said, you can't do this. You can't do 5,000 grams. But this system can do that. Even if you don't get the R&D, you can do better than, you can do about 4,000 grams per kilowatt. And then these other numbers you've seen before. So who are we going to sell it to? If you try to sell it to the power grid of the United States and compete with coal at 5 or 6 cents a kilowatt hour and win 7 cents a kilowatt hour, or whatever those numbers are, you're dead. You can't do it. So why do we have to sell the first one? I'm not talking about the ultimate system, but why do we have to sell the first system to the low cost? Why not sell it to the high cost? Well, for example, I poked around the web. The highest price electricity I could find was in 2008 for industrial users in Italy, 29 cents a kilowatt hour. If you can sell the power at that rate, and you can get the maximum power that you can theoretically get out of there, you're going to make about $78 million in a year, which will pay for your launch in about 1.5 years or so. That's not too bad. Okay? Now remember, you still have to pay for the satellite. I don't know how much it's going to cost. A lot of places in this world, if you want electricity, what you do is you get a diesel generator and you import diesel fuel. And the most expensive diesel fuel I could find in the world in 2009 was in Malawi at 42 cents a kilowatt hour. Now, I'm sure this number is larger today, okay? But if it's still that, we can basically pay for a launch in 1 year, give or take. And finally, as some people have suggested, the military is interested in buying power in places where the fuel trucks get ambushed. You cannot ambush an IR beam, okay? And they are willing to pay probably at least a kilowatt hour, in which case you can pay for your launch in 6 months. Next slide, please. Okay, here's why this might work. For the first step, I'm not talking about the ultimate system, but the first step. If you can't do the first step, you can't do the 100th step. And the problem with space solar power is for 30 years, we have been not taking the first step. Because the first step isn't studies, there's nothing wrong with studies, or even experiments. The first step is a satellite up there that's selling power to customers, any customer, anywhere, at something, let's just say not losing too much money, okay? You do not need construction because the whole thing is one launch. It's just like any other satellite launch. You build a satellite, you fold it up, you stick it in the launch vehicle, you put it up, you unroll it, you operate it. It's the same basic idea that we do all the time. You don't need frequency allocation because IR doesn't interfere with communications. That might actually not be much of an issue anyways. You don't need a 10-kilometer chunk of land. You need a football field. Okay? The top of a good industrial building, you know? And you don't need advanced launch. The launch vehicles that are sitting on the ground ready to go up today and which will probably be ready in a few years are acceptable for this approach. Next slide, please. So, this is a weekends and evenings project. And not a huge amount of effort has gone into it because I have a day job and I have to pay for a couple kids in college and stuff like that. But here's some of the work that needs to be done. If anybody would like to help me, you are welcome. The first is we need to achieve the target efficiency. Some of those will be done for us, but the ability to send, you know, laser power from here to there will not. There's a laser mode is trying to find ground applications for that. But the beam combining system, you need to put the beam all together and you need to get some losses there. There's some experiments that say we should be able to do 90%, but that's just experiments. The beam aiming system, I think I know how to do this, but it'll have to be the subject to the next paper because there may be a better way or I may have not thought of something. The sail, the bit that collects the energy, deployment, solar sails are notoriously hard to deploy. Manufacture, it is going to be very difficult to build this thing. You need to have a couple 100-meter thing with one side covered with solar cells on the electronics to get the energy from here to there, the other side covered with fiber lasers and the pumping lasers and the heat rejection system. This is not going to be easy. And there may be alternate stiffness approaches for less mass, which would be great. Orbit maintenance. I've done some simulations of this. This is a very lightweight vehicle. The sun is going to blow it around. I mean, it's derived from a solar sail, which uses the sunlight for propulsion. It looks like it's not too bad, but you're going to have, you may just you have to allow it to move around in geosynchronous, but you'll probably need some orbit maintenance, probably some sort of electric thrust vehicle. Environmental and safety studies. You know, you're having this 6-megawatt IR beam coming down to Earth. There might be some issues, who knows? That needs to be investigated. I'm a little worried about the bird's eyes, actually. And of course, there are thousands of smaller issues that need to be dealt with. Next slide, please. So, conclusion. You can make an argument. It may not be a correct argument, but it is a plausible argument that there is a fairly short R&D path between where we are today and a small, one-launch PowerSat that can sell power in niche markets at something vaguely resembling a profit. Maybe not just losing too much money. It's based on these things I've been talking about. It's plausible, I'm not saying it's necessarily true, it's plausible that it's competitive with nuclear on an installation cost per watt. It looks like it might conceivably be competitive with diesel in some very remote regions. And I believe that as part of an energy portfolio, you should have some slam dunks, things that are easy to do, that's going to get you a little bit, and you should have some things that you're swinging for the bleachers, boy. It's really hard. You may strike out, but if you hit, you win the game. And I think SSP is in that category. I think it's significantly superior to fusion, and fusion gets a whole heck of a lot of money, and we don't get dilly squat. Thank you very much. Payoff, even though there's a huge payoff. And what I'm trying to do is show that they're wrong, even if not all my numbers are correct. And I'll tell you right now, they're optimistic. So there's 3 technologies it takes advantage of. A solar sail, developed by Japan, in orbit, on its way to Venus today. We know it works. Infrared power beaming, which has been demonstrated at small scale by this vehicle here, and fiber lasers. So next slide, please. So here's how I see the SSP problem. It is a high-risk, huge payoff energy investment. It's high risk because it's difficult, it may fail, could cost a lot of money, but if bit has been demonstrated in many frequencies and over different distances, yet for some reason, that's what we spend on the research in the federal government. It's more in Japan. So what I'm going to try to do here is show you that if you look at a simple single launch system, that there's a fairly minimal R&D program to get you ready to start building it. And the target that I'm aiming for is 100 grams per meter squared of collecting area, 10% end-to-end efficiency. One Falcon 9 launch, modified for the Heavy, because I found out, fairly recently. If you work through the numbers, and if I haven't made any terrible mistakes, which is there's no guarantee is the case, you get 120 meter radius sail with thin films using fiber lasers for IR beaming. You get a figure of merit is mass per unit of power to the grid, because that launch cost is a big piece. So we come up with 720 grams per kilowatt, get about 6 megawatts to the grid, and the idea is if you can sell that to certain high-priced niche markets, that you can pay for the launch, because I know how much the launch costs. I don't know anything else. You can pay for the launch in a year, give or take, and you don't want to start until R&D on the ground has got you about a factor of 5 better, and the efficiency that it works. We get all the power we could possibly want for billions of years. Okay? There are two classes of energy research in this area. There's fusion, it's also very high risk, high payoff, and SSP. Fusion has been going on for decades. They've spent tens of billions of dollars. They spend about $100 million of federal government money a year. They have never produced a single watt of power above what has come in. And if things go really well, I'm now Globus, and I did some of this work with some collaborators in Romania who were involved in the Space Colony Contest. And I'm going to give a talk which is the exact opposite of the one you just heard, which I thought was great, by the way. He was talking about this enormous project that looks really cool. What I'm interested in is what is the smallest possible project, space solar power project, that could possibly turn a profit, and how much R&D do we need to get there? And the reason I'm interested is that the folks that criticize space power, at least some of them say, you shouldn't even put in R&D because it's so hard and we need so much R&D that it can't possibly